All right, let's learn about anion gap today. I welcome you to join me in this thought experiment where imagine there is a bucket and the bucket has red balls and black balls. You don't know how many. What you know is they're equal number of red balls and equal number of black balls. At random, you pull out a few balls, just so happens to be 20, and let's say 12 of them were black balls and 8 of them were red balls, right? The difference here is 4, right? I'm willing to accept that the difference in the red balls and the black balls in the bucket is also 4 because I started with this premise that the number of black balls and red balls were equal in the bucket. If I pulled out 4 excess black balls, that means there are 4 excess red balls in the bucket. So the difference of my measured balls, the ones that I counted, and my unmeasured balls, the ones that I did not count in the bucket. And if you think the color of the balls as like positively charged ions and negatively charged ions, the whole bucket as a human body, then when you do EBZ and you count positively charged ions and negatively charged ions, sodium and potassium, we sort of ignore potassium because it's so little, but then sodium and chloride and bicarb. The difference between these two has to be the difference between whatever positive charge and negative charge exists in my body, although I did not measure them, right? And that is why anion gap is called excess unmeasured anion, right? It is the excess, meaning more, unmeasured, anion meaning negatively charged ions, right? And the presupposition that there are equal number of red balls and black balls comes from the fact that we are electrically neutral and the number of positive and negative charge has to be equal in our body, right? The other way of looking at it is using this chart here. Imagine there was a magical way of like measuring all the unmeasured cation in my body. I'll label here unmeasured cations and all the unmeasured anion in my body and calculating that difference, right? I'll get this difference labeled anion gap here. I don't have that magical way, right? But I can measure all the sodium, chloride and bicarb, and the difference is still exactly the same, right? And that happens to be mathematically correct because total number of positive charge and total number of negative charge, so these two columns, are equal, right? That is one way of looking at it. Now, one more thing to understand about anion gap is a normal anion gap of 8 to 12 means that there are 8 to 12 negatively charged ions in my body right now that I have not measured, that are in excess to the unmeasured positively charged ions in my body right now. So unmeasured anions are more compared to unmeasured cations in my body by 8 to 12 if my anion gap is normal, right? What that supposes is 4 of those unmeasured, right, are albumin. Albumin are negatively charged. I've not measured them. For a normal human being, an albumin of 4 is normal, right? Imagine a scenario where a cirrhotic with albumin of 1 comes with decay. It sounds like the person has type 1 diabetes mellitus, the person has abdominal pain, the person has low pH, the person has high glucose. You are thinking decay, but when you measure the anion gap comes back 30, you look at the albumin is 1. If you correct that gap for albumin, the gap goes to like 20.5 or something like that, right? There's a way to calculate that, and you need to calculate that, especially if you are expecting a high anion gap and their anion gap happens to be low. That is because your presupposition there is wrong. One of the presuppositions at least was that they have albumin of 4 when you thought that anion gap of 8 to 12 is normal. So that is how you think about it. Thank you.